All right, can you guys hear me okay? Okay, great. All right, well, I appreciate everyone's flexibility and meeting this morning. And we'll do our lecture, and then next week everything will be, I assume, schedule will be normal and everything. So, but anyway, we'll do our lecture today. Okay, so we left off yesterday, and we were talking about linear regression and matrix notation. And we said what we want to do is we want to do, we present fitting a linear regression line in matrix notation. We said basically the line that we're going to fit is going to be x times w. And what we said was we have a loss function that we want to minimize, right? So there's a loss function, an objective function that we want to minimize. This loss function represents the sum of squared residuals. And so we said we can take the difference between the actual values t and an x and the predicted values xw. And when you take that, let me just pull up yesterday's notes as well. This was yesterday's notes. We said, we're gonna say our loss function is the difference between the actual values, the target values t, and our predicted values, which are xw. And we said, well, if we take t minus xw and we want to kind of square them and sum them up, right? T minus the predicted values squared, we can turn this into matrix notation, and it looks like this. And so our loss function looks like this. And if we expand out our loss function, if we go through the entire process of expanding our loss function, it's going to end up looking like this. And so this is kind of where we left off, or I guess we went a little bit further. We don't exactly leave off here. So we took the difference between, sorry, this is, you just hear some beeps for a few seconds here. Okay, all right, that's the laundry saying it's done here. Okay, but anyway, so we take the difference between the actual values and our predicted values. These are our residuals, we square them. And because it's matrix notation, this operation will effectively sum up all of the values. So we're gonna have the sum of squared residuals. We can expand out the multiplication into all of these terms. And we said, what we want to do is this loss function, we're going to treat the actual values and the x values as fixed values. And this loss function is just a function of the weights, the intercept and the slope parameters. Okay, so that's what the W kind of stands for. It's the weight that we're going to put on the intercept and the weight that we're going to put on the slope. It's going to be a function of those terms. And so what we want to do is we want to take basically the derivative or the gradient of this with respect to W. We set it equal to 0 and we solve. And so this was kind of our helpful guide for figuring out gradients with respect to W, because our output function is a single scalar value. We want to take the gradient of that output as W changes. And so when we go through that process, if we take the gradient of the loss function with respect to W, this is what we get. The gradient of T transpose T is 0. The gradient of W transpose X transpose T is just going to be X transpose T. And the gradient of W transpose X XW is going to be 2 X transpose XW. Okay. And then, and again, this is what we have so far. We're going to set this equal to 0. We solve, and to solve, we multiply. We get rid of the X transpose X by multiplying by the inverse of X transpose X. So we have X transpose X inverse. And therefore, our solution is going to be X transpose X inverse X transpose T. And this is going to be the values of W that minimize the gradient. I mean, not the gradient, that minimize the loss function. Okay, it's where the gradient is equal to 0. So I think this is where we left off yesterday. And so we'll kind of explore this a tiny bit. Okay, so here is a very, very, very simple data set. X is 1, 2, 3, 4, and the target values are 1, 3, 2, 4. Okay, so I've got X is basically I have 1, 1, 2, 3, 3, 2, and 4, 4. And we say, okay, what is the best fitting line? The line that will minimize the sum of squared residuals, or minimize the mean squared error here. Okay, and so here I'm going to create X. X is going to be, we're going to create a column of ones, and the X values 1, 2, 3, 4. So I'm just doing C bind, and we can take advantage of the fact that R recycles values. So I can just do C bind 1 along with X, and that's going to create this. And then I can do X transpose X, because remember, the solution is going to be X transpose X inverse X transpose T, T being the actual values, 1, 3, 2, 4. So I have X transpose X. So if you do X transpose X, you're going to get a 2 by 2 matrix, 4, 10, 10, and 30. And then we're going to inverse it. The inverse operation in R is solve. So we have X transpose X inverse. That's going to be solve this. This is going to be another 2 by 2 matrix. And if I do X transpose X inverse X transpose, that ends up being a 2 by n matrix. And if I multiply that by T, which is n by 1, okay, the result is going to be our W hat. So this is X transpose X inverse times X transpose times T. And so the result of that is a 2 by 1 matrix, which represents the coefficients W0 and W1, our intercept and our slope. So it says the estimate for the intercept is going to be 0.5, and the estimate for our slope is 0.8. And that's going to be the values of the intercept and slope that minimize the sum of squared residuals if we were to fit a straight line to this data. Okay, and just to kind of verify that this indeed is the best solution, we can also just fit the data T to X using the linear model function, and LM in R says the intercept is 0.5 and the slope is 0.8. Okay, so we did matrix operations, we got 0.5 and 0.8. LM and R also gives us 0.5 and 0.8. This is the answer. And if we were to use any of these other values and things like that, we would also result in the same 0.5 and 0.8. And this is a little bit trivial just because linear regression is already a bit of a solved problem. We already know how to get the optimal intercept and the optimal slope. But my hope is to just kind of show that, by framing it as an optimization problem where we are trying to minimize the mean squared error or the sum of squared residuals, we can see that the resulting kind of matrix operation results in the correct values. If we want to figure out the prediction, we can just take the new input values, or I guess even our existing input values, X, and multiply it by the fitted slope and intercept. So we have W hat, which is the values that we fit, the intercept and slope. So I do X times W hat, and this gives me T hat, the predicted values. And when we do this, I get 1.3, 2.1, 2.9, 3.7. These are our predicted values, and I can plot them. And this would be the line that we have predicted, okay? And so we can see we got little residuals here, and apparently this line will minimize the sum of squared residuals, okay? So this is what we have, okay. So let's just try this on something that's not as much of a toy data set. So we'll take a look at the Olympic data set. So same, so we saw this again, this is the track and field 100-meter foot race in the Olympics. And this is the gold medal time. And so if we did LM, it says our intercept is 36.309 and the slope is negative 0.013. Okay. And again, the intercept doesn't really have a practical interpretation. This the practical interpretation would be the winning race time in the year 0. If the year, and I guess there was a year 0. I don't know if they had an Olympics in the year 0, but but according to our linear model, the winning race time would have been 36 seconds, and that's probably just not true. So, but again, we don't want to extrapolate. That's kind of one of the rules, right, of linear regression. Don't extrapolate. So we're going to just say this is a good way to predict from, say, 1900 to 2000-ish. Okay, so what we'll do is we will do the matrix operations. And so again, I'm going to take my X values, which apparently goes from 1896 up to, I think, 2004 or 2008 in our data set. Let's see. Maybe 2012. Okay, 2004, 2008, 2012. So we'll take those values. We create a column of ones. So I'm going to just bind 1 to our X values. And then we'll go through the process and we'll do X transpose X inverse X transpose T. So I'm just going straight there. I got X transpose X, put it inside solve to get X transpose X inverse. And then we have X transpose times T, and we're going to just take the actual values, the time, and turn it into a matrix. So I got X transpose X inverse times X transpose times the column T. And what it does is it says, okay, your estimate for the intercept is 36.309. Your estimate for the slope is -0.013. And if I just go back a few slides, we can see, yes, this matches up exactly to what we have, 36.309 and -0.013 for the slope. Okay, so our values here match exactly what we got with the linear model. Okay, all to say, whatever we're doing with the matrices, it's still working. So that's good news. Okay. All right. Let me give you our first view quiz answer. And so this one again is week 1 Thursday view quiz, and the first answer is E as an elephant. E as an elephant. I just want to make sure when you're filling out your view quiz answers, not to get them mixed up. So week 1 Thursday. E as an elephant. Okay, if you've already done yesterday's view quiz, then there's no problem. But just double check that it's for week 1 Thursday. E as an elephant. First view quiz answer. Okay, and again, to fit our predicted values, I can just take our input values X, which again is the column of ones along with the column of the years, multiply it by our estimated intercept and slope. And these are the values that we get. And if I plot that, this is the line. And it looks like, oh, okay, that seems like it's doing a decent job. Okay, so this is the fitted regression line to our data. Okay, so far so good, I believe. And now we say, well, what if we wanted to fit something other than just a simple straight line? What if I wanted to try fitting something with a curve? Okay, so we look at this, we might say, well, you know what, I don't know if I want to use a straight line. What if I want to use like a quadratic term? Okay, and so if I wanted to add say polynomial values, I can expand our X matrix. I could take X, which is currently the year in which the Olympics were held, right? 1900 to 2000-ish. So 1896 to, I think, 2012. We can take that column and we can say, you know what, I want an X squared term. So we're going to take the year and we're going to square it, which is a strange thing to think about, right? What does it mean to have the year 2000 squared? And I don't really know, but we're just looking to see if there's some kind of maybe a quadratic relationship to maybe time, right? Maybe the times are improving at a kind of a different rate, not this constant thing where, every 4 years the winning race time drops by 0.05, but perhaps in the beginning it dropped much faster, and as time has gone on, maybe the amount we're dropping reduces and things like that. Who knows? Okay, we just want to be able to fit something a little bit non-linear. So we'll still have a column of ones for our intercept. a column for our slope and a column for a quadratic term. So we're going to take our values x and we're going to square this. Okay, and so I can do this easily, and I can just take the column year, and then I'm going to just create a new matrix x. And for the new matrix x, I'm going to create a column of ones. I'm going to create the column x, and then I'm going to just take x squared, and I'm going to just put that in here, right? And so we're getting really big numbers, because if you do 1896, what is this? 1896 times 1890. Oh dear. 1896 times 1896. You get 3,594,816. Okay, and so just looking at the first 6 rows in our data set, we're getting these really big numbers. Okay, but it's fine. Let's see if we can do this. And so if we say, okay, well, what would our fitted values be? We've got W0 plus the W1, kind of our slope term, times xn. And then we've got W2 times our xn squared term. So we have our x squared terms, and we're going to have W2. And if we say, well, W is going to be a matrix with W0, W1, and W2, we can say, well, this is still W transpose xn, right? Because xn consists of 1, xn, and xn squared. And if W is W0, W1, W2, if we do W transpose xn, we're going to get this thing. So we're going to use the same formula that we had for the simple linear regression model. We don't need to change anything up here. And because this is the same formula, okay, all right, the predicted values are still going to be x times W, our matrix x times our matrix of weighted values, W0, W1, W2, I mean, our matrix of weights, the intercept, the slope for the linear component, and the kind of the coefficient for the quadratic component. Right, and all of this gives us a bunch of predicted values, and this matches exactly what we want. So we still have, we're going to use xw to say these are our predicted values. Okay, so far so good, and we can see that this will just generalize to any arbitrary number of columns. If I just keep adding w terms and I keep adding x values and columns in my x matrix, we can just see that xw still generalizes to all of this. And so because the predicted values are given by the same operation x times w, the loss function, or our objective function, the mean squared error, is still exactly what it used to be, t minus xw transpose t minus xw. Okay, and so this is kind of the reason why we like to use matrix operations in linear algebra for so many things, is because we no longer have to worry so much about individual terms. Is that once you put them in matrix notation, you can kind of expand and generalize kind of the number of columns to some arbitrary number of columns, and these things will still remain. And so what is the solution for this? Well, because this thing remains exactly unchanged, when I say, you know what, let's find the value for w hat that's going to give us the best predicting coefficients, the coefficients that best predict our model, it's going to be exactly the same as before. It's still going to be x transpose x inverse x transpose t. We can go through the same exact process of taking the gradient, setting it equal to 0, and solving, and we're going to end up with the same solution. And that's a nice thing, because if we looked at each term individually and we did partial derivatives, we would have additional terms to solve for, right? We would have w0, w1, the partial derivative with respect to w1, the partial derivative with respect to w2, so on and so forth, and you'd have kind of this fairly complex system of equations to solve for. I mean, some of these things would drop out and cancel and make it a little bit easier, but it's still a little bit more of a pain to have to do individual partial derivatives. With matrix notation, we can just use the same operation before, and we've got the same. Okay, so this is what we have. All right, and so we say, well, let's try this out. Okay, so if I say, let's take my matrix X. So again, my matrix X is the column ones, the column of the year, and the column of the year squared. And if I say, let's do X transpose X inverse. So I have X transpose times X inverse times X transpose times T. I actually run into an error. I get error in solve.default. Okay, so where's the error running into? Okay, it's running into an error in this operation here, the solve. Okay, and so we can see, when we do X transpose X, there's actually, solve is a S3 object-oriented thing, and so there's solve.this and solve.different things, but the default method, it's trying to figure out the inverse of the matrix. And we get this error. It says system is computationally singular. Reciprocal condition number equals something. Okay, so computationally singular basically is an error you get when it can't find the inverse of a matrix, right? And there's, you might have learned about this in linear algebra, but in some matrices don't have inverses, right? Because it's kind of like almost like dividing by zero type of thing. But that's actually not what's going on, okay? So what we're running into is, if we look at this matrix, okay, because it's trying to solve the inverse of this matrix, X transpose X, right? So X transpose X, X transpose X. When we look at that, we have a 3x3 matrix, okay, because X is what, I don't know, 28 rows, 3 columns. And so if you do X transpose X, you're going to get a 3x3 matrix. And if we look at this last term, what do we have? We have 4.094 times 10 to the 14. Okay, can you guys see where we might be running into a problem here? The issue is that this number is just really big, okay? The issue is that this number is really big. And so when we are trying to inverse the matrix, okay? So when you try to inverse the matrix, you effectively have to, do some division by some of these terms. And, when you take the column X and you square it, because the numbers are like, say, 2000, right? It's the year 2000, the year 2000 squared is 4 million. And then when you do X transpose X and you kind of multiply those things and you sum them up, we end up getting huge values, something on the order of 10 to the 14, right? 10 to the 11, 10 to the 14. This column ends up being really big. And so, when you find the inverse, okay, if at some point finding the inverse of a matrix involves dividing by the determinant of the matrix. And because this number is so big, we're basically creating these tiny, tiny numbers. We're trying to divide by such a big number that the resulting number ends up being smaller than machine epsilon, right? And so we're running up against kind of the limits of floating point arithmetic, right? So this is where all of these things kind of come into play, because last quarter in 102A we talked about floating point numbers, and we said, and part of you might have been wondering, like, why is this important? And like, why do we need to worry about this? Well, we run into situations like this. This is not an uncommon thing. I mean, it doesn't happen all the time, but sometimes you run into problems and you wonder, like, this, I feel like it should work, okay? And chances are you're running into some kind of floating point arithmetic, right? Problem. So when you're trying to divide by a really huge number, we run into basically some computational instability here. The computer says the matrix inverse doesn't exist, but that's just not true, okay? It actually does exist, it's just, it doesn't know how to compute it because we're getting numbers that are way too small. So there's a bunch of stuff that we can do. One thing that could make our life easier is we can just take X and we can just say, let's subtract 1900 from every single number, okay? And every single number will become a lot smaller, right? We'll get -4, 0, 4, 6, 8, 12, and we'll have smaller numbers, right? Another number is we can just say, well, you know what? Let's just take this last column, X squared, and let's just, rather than having really big numbers, let's just divide everything or multiply everything by 0.0001, okay? And so I'm just rolling the decimal place 4 places to the left, okay? And so now I have 359.48 and 361.00 and stuff like that. I don't have to worry about us running into a huge thing, right? So this is just one possible solution. There's all kinds of ways to deal with this issue when you have numbers that end up being too big. So all I'm doing here is I'm going to just take x squared and I'm going to scale them. Okay, so I'm creating a new matrix called x scaled. Okay, and it's going to be 1x and x squared, where x squared is just 0.001 times x squared. Okay, and then and now I don't run into any problems. I can do x transpose x inverse, all right, using my x scaled matrix. So x transpose x inverse, this doesn't produce an error, times x transpose times t. And this works just fine. Okay. Does that feel okay about what I did and how I got around some of our computational issues? And this doesn't affect, I mean, it affects the size of our coefficients, but it doesn't affect necessarily like the solution itself, right? All we've done is we've just scaled. It's like it's like instead of measuring values in millimeters, we're measuring them in meters is effectively what we're doing, right? So instead we're just changing the size of the unit. Because if you measured things in millimeters, you know, you might have really big numbers, right? What's, you know, what's the, how tall is someone in millimeters? And I don't know, like 1,800 millimeters or something versus 1.8 meters. Okay, and so, and again, just to kind of show that our coefficients using the matrix operation, x transpose x inverse, x transpose times t matches what we would get using LM. I can say, well, let's do LM where we're going to predict time based on the scaled operations. Okay. Now, one thing, are you guys familiar enough with R's LM function to understand what the 0 plus means? So in formula notation in R, by default, it's going to try to fit a coefficient for the intercept. Okay. And it's assuming you don't have a column of ones. But in our case, our X matrix, X scaled, has a column of ones already. So we don't need to fit a separate intercept. So when you do 0 plus will not bother fitting a separate intercept term. Okay. So here we're going to do predict time based on the X scaled matrix. And so the coefficients I get are exactly the same that I got using my matrix operation: 396.328, negative 0.382, and 0.944, which is what I have here: 396.328, negative 0.382, and 0.944. So this this matches up, and that's good news for us. That's good news for us. Okay, let me go ahead and give you your second view quiz answer for today. Second view quiz answer for week 1 Thursday is A as in apple. A as in apple is your second view quiz answer for today. Okay, and then and if we wanted to fit the values, all we do is we do x times w hat. Again, x times w hat. These are fitted values. And here we go. All right, and so now we have a quadratic fit, and we can see there's a little bit of curvature, and perhaps this will do a better job or not. It's hard to say. It's really hard to say just looking at this window of time, especially because we don't really know what the future holds. So maybe it levels off. Maybe there's a limit to how fast humans can run, or maybe it will continue to incrementally get faster, and perhaps a quadratic term is not really the best. And, you know, I kind of almost, looking at this data, I kind of want to throw this number 12 away because this was measured in 1896. And if you look at the data, I think there was just a limitation in timing technology at the time. Because now we measure to the fastest, like to the one, like 0.001, right? We measure to like the thousandths of a second, and back here it was measuring to tenths of a second. And I think in the very first Olympics, they measured to the nearest second. And I think they realized, oh, you know, we need to do a little bit better than that. So who knows if it was really 12 seconds or not. There's quite a bit of error. So anyway, this is what we have. Okay. I don't know if you are familiar, but there is a function called poly, okay? And what this poly function does is it creates uncorrelated values, okay? So one thing that we've done, so the way we did this is we took basically our x values and we just squared them and I scaled them down, okay? Well, I don't know. In your linear regression course, or maybe 100C, did they talk about using this function poly as a way to avoid high correlation between powers of the thing? So if you take x, let's say x goes 1 through 100, and then you have x squared, and then if you have x cubed and x to the fourth, okay, you're going to have basically all of those values just are incredibly highly correlated, right? Just as x gets bigger, everything else gets bigger. And so everything has, it has high correlation. And if your values are too highly correlated, that introduces a whole other host of problems, right? You've got your coefficient estimates become unstable and things of that. Does that sound familiar? If all of your variables are highly correlated. So one thing is we have the function poly, okay? And so what poly will do is it basically introduces other terms so that at least for the range of the variables, the range of x, the values are uncorrelated. Let me see if I can kind of just illustrate what this might look like. And I think something's, give me a second. Let me share my other screen. Are you guys able to see this thing? Okay. So what poly does, right? Okay. So normally you'd have like x this, and then x squared looks like this, and x cubed, and x. So this actually, so it looks kind of like this, right? So you'll have x squared, and x cubed, and these are all end up being highly correlated. When you have poly, at least for the range on x, okay, you'll have this, and then x squared will be like this, okay? So this will be kind of your x squared term, and then x cubed will be cubic, and it will be the column of x and x squared and x cubed. You know, you got these values here. The correlation between each of these things will be uncorrelated. Each column is orthogonal. All right, and the effect of that is when you fit this, you will avoid finding just some like if let's say the true fit is linear, okay? If the true fit is linear, you'll still find some correlation between x3 and x, right? Like the cubic value and x. You know, if the true fit is linear, there will still end up being kind of a term where x cubed is maybe not significant, but there's still going to be some kind of fit between the cubic value, just because the linear fit says, you know, as x gets bigger, you know, y gets bigger, and there's going to be some kind of fit where, you know, if the cubic term gets bigger, y also gets bigger, okay? Whereas over here, because these things are orthogonal, you're only going to find whether there is a cubic relationship or not, or whether there's a quadratic relationship or not. So using poly can help avoid some of those situations. Okay, so we can do this simply by just using the function poly, and we can say I want quadratic terms. So we're going to take X, which is the year. We're going to fit in a column of quadratic terms, and so here we have a linear values and quadratic values. Okay, so what it does is it scales all of the values. So again, year started off at 1896 and ended up at, say, 2008, and it just kind of scales these. And here it picks the numbers for you. And so it says, okay, negative 0.306, that's going to be the 1896. And as the years go on, they get progressively larger. And so we can say, you know what, fit time to our quadratic fit. Okay, here there's no column of ones, so we don't add the 1 0 plus 0. So I'm going to do fit a polynomial of degree 2, and we get this, and we get the intercept is this, the linear term is this, the quadratic term is this. Okay, and unfortunately, we lose a lot of interpretability. All right, because we're not quite exactly sure what this negative 2.53 means in terms of whether in terms of the linear fit here. Okay, so we lose a little bit of interpretability, but we can still figure out the fitted values using the linear model. So we can do LM $fitted values. There's no need for any kind of matrix multiplication here because it's all stored when we do LM. And so these are the fitted values. And if we look at these fitted values, 11.322 and 11.228, these are the same fitted values that we got when we did a quadratic relationship, 11.322, 11.228, 11.1366. These are the same values that we get when we fit a quadratic relationship. Okay, so again, an unfortunate side effect of using poly is that because all of these X values get transformed, and the interpretation of the coefficients is a lot harder. Okay, but I would say poly is still very useful in that we can kind of compare polynomial fits of different orders, and we can rapidly fit a whole bunch of different models, say a quadratic and a cubic and fourth order and fifth order polynomial and things like that. And we can compare the resulting fits even if we lose some interpretability. So I'm going to just rapidly fit a third order polynomial, fourth order polynomial, fifth order polynomial, and sixth order polynomial. And I can just do this by saying I want to find a linear model fit between the winning race time and the year X, but transformed into third order, fourth order, fifth order, and sixth order. So poly X6 will create 6 columns. It'll create the linear column, a quadratic column, cubic column, fourth order column, fifth order, and sixth order column, and they're all going to be uncorrelated. And here I'm going to go ahead and I'm going to just take the fitted values and I'm going to plot them in different colors. Okay, so we have the original values will be dots, and then the linear model will be red, the quadratic model will be orange, cubic will be green, fourth order will be blue, fifth order will be purple, and the sixth order will be dark gray. And this is the resulting fit. And so let me just kind of zoom in here. All right, so we can see the linear model is red, and then we've got a quadratic in orange, and a third order in green, fourth order in blue, fifth and sixth order in purple and gray. And, in this middle part, it's kind of hard to see, is there much of a difference here? We can see that as we increase the degree, it does a better job of fitting this one kind of outlier out here. Okay, it's able to kind of accommodate and reduce the residual for this one outlier. and how does it fit everything else in here, because there's a bit of jitter. It's hard to know. Okay, so which of these say does the best job? That's kind of the question that we want, which is the one that we want to fit. Okay, so in kind of 101A, your traditional approach would be you'd look at the summary table and you'd compare a few different things, right? You'd compare perhaps the AIC or BIC values or different things like that. You'd look at the kind of the summary table. So here's the summary table for the cubic fit. And we see, okay, well, the intercept is significant. The linear component is significant. And the quadratic and cubic components are also significant at the 1% level, right? We got 2 stars here. So these are all kind of significant. And so we might say, well, let's keep the cubic order or something like that. Okay, I don't know, right? If you look at your R squared values, we have 0.8973. Our R squared value is 0.8973. And there's other terms that we could look up. All right, if we look at the summary for the 6th order polynomial, okay, the 6th order polynomial, the first 3 terms are significant, I mean the first 4 terms, the intercept along with the linear, quadratic, and cubic things are all significant, but the 4th, 5th, and 6th order terms are not significant at the 5% level, so perhaps we don't want to keep them. We do see our R squared values is higher though at 0.9233. Okay, so our R squared value is higher versus this one, only a little bit. And there's other kind of tools that we have at our disposal for deciding which of these things are best. Okay, and this is kind of the the crux of the problem is, how do we measure model performance? And it's not always straightforward, right? If you only look at the R squared value, I think we know that the more terms you fit, the more complicated your model gets, your R squared values can kind of keep climbing, right? You can keep adding more terms and you're going to be able to fit some of these extreme values. And you can kind of always reduce the amount of residuals left over, right? And so if you only look at the R squared model value, the more complicated models will always kind of outperform. We can look at the summary tables and we can see that some of these higher order components are not significant at the 5% level. And so the question is, would we just take the 3rd order polynomial and say, all right, that's the one we keep and we're done, okay? And the answer is I don't know if that's the best solution. And so I guess we'll wrap up just a touch early today, but what we're going to look at next week is we're going to use cross-validation as a way to assess model fit. So rather than relying on these summary tables, which don't get me wrong, I think summary tables are excellent. And if you feel like you can interpret these things and understand them, absolutely go with it, okay? But what we are doing is, we're going to do a little bit more machine learning, right? So less human interpretation and less human decision making, and a little bit more turning over the decision making over to just kind of algorithms, so that we can just kind of say, hey, computer, make these decisions for me, okay? And we're going to do that using cross-validation. So next week, we'll take a look at cross-validation, where we're not going to have to look at these summary tables and use our own kind of interpretation, but we're going to kind of turn some of the decision-making over to just a way to assess another, I guess, set of how well did our values fit, okay? And that's going to be cross-validation. We'll introduce that on Monday, okay? So that's where we're going. Next is how do we measure model performance if we have different models kind of competing that could work. We're going to do that with cross-validation. Okay, let me go ahead and give you your last view quiz answer for today. The last view quiz answer for today is D as in dog. D as in dog is our last view quiz answer. Okay, and we will end here for today. Thank you all for attending. I appreciate your flexibility. Those of you who are watching online, thank you for watching online. And please just double check and make sure you are filling out the correct view quiz so you get the appropriate credit. And other than that, have a good rest of your day. Have a good weekend, and we will see you on Monday. And I'll have office hours from now, I guess, until I think 11:30, 10:30 to 11:30 is my new office hours. All right. Thank you, everyone.